Okay. Right. So the Bayesian rule is actually a very it's very analogous to what we are actually going to introduce here. So the concept I want to introduce here is called importance sampling. So the importance sampling is the idea is to focus on the important areas. Okay, and this is a very, very useful technique for computing low likelihood events. So, for example, let me figure out a very simple example. Okay, so imagine I want to compute the probability of an event A that is very, very less likely to happen. Okay, but there is another event B. So AA is a low likelihood. Okay, and computing IA is also expensive. All right, but there is another event B. Oops. Computing event B is another event is an event that is highly correlated with A, and computing IB is much less expensive. All right, so this is like a discrete analog of our previous case, right? So in the previous case, we know that as we go towards larger t, small delta v, we are more likely to fail, right? So in this case, I can, for example, quantify my b to be just a certain region of the probability space, right? So maybe this is my b. So if my delta t is greater than, for example, if my delta t is greater than this value and my delta v is less than this value, I can say, okay, it's actually more likely to fail, and that's my event b, which is much easier to compute. It doesn't require me to perform any simulations, right? Then, what's a good way to compute the probability of A rather than just directly sampling many random samples and look at how many has failed? Yeah, the probability, what if I can compute the probability of A given B? So the probability of A given B, given that A and B are very highly correlated, should be probably much larger than the probability of just A by itself. So if you can compute the probability of A given B, you probably have a lot higher relative level of confidence than directly computing the probability of A, right? Okay, but how do I go from the probability of A given B to the answer we want to compute, which is the probability of A? Can you say again? Sorry. But so the probability of A given B and
is probability of A.
Probability of A times probability of B.
No.
A and B divided by probability of B, right? So you are saying this is equal to this, but we want to get to this. This is what we want to compute, right? We want to compute the probability of the failure. So this we know how to compute. We do that, right? But how do we compute this?
Probability of A given B times probability of B plus probability of A given not B times 1 minus probability of B.
So yes, you have given the correct formula, but I want to explain in detail how that comes from, right? So let's actually derive the formula you just spelled out. The probability of A is equal to the probability of A and B plus the probability of A and not B, right? I wrote B bar as not B, right? So probably A happens if A happens and B happens, or if A happens and B doesn't happen, right? So that's simple. And let's now use the formula you just told me. So probability of A and B is actually equal to the probability of A given B times the probability of B plus the probability of A given not B times the probability of not B, right? Okay, now we have an equation that we can potentially use in our Monte Carlo method. And using this equation, it can be many thousands of times cheaper than directly compute the probability of A. Why is that? First of all, because the event B is very easy to determine. We can actually use a lot of samples to nail down the probability of B and probability of not B very precisely, right? Okay, so these are not a problem because this doesn't involve my very expensive simulation. And now my simulation only falls into determines the two conditional probabilities. Okay.